Okay, the final speaker for this session is Shiraz Minwalla, and he's talking about PP wave string interactions from Yang-Mills theory.
Okay, it's very nice to be here, and I thank the organizers for the opportunity they've given me to talk here. Okay, so I will be talking about ways of getting interactions when studying strings propagating on the PP wave background, ways of deriving interactions of these strings from Yang-Mills theory. Okay, my talk will be based on work done in collaboration with 6 other people: Neil Constable, Daniel Friedman, Matt Hedrick, Lubosh Mottl, Alexandra Postnikov, and Witek Skiba. And most of what I say is based on this paper here. Some of what I say is also based on work in progress that has not been published. Okay, so this is a brief outline of my talk. I'll first start with a lightning review of the BMN proposal. I will then explain how non-planar graphs survive the strict n goes to infinity limit when it's taken in the BMN sense. And this will perhaps be in slight conflict with usual intuition about the n goes to infinity limit. I will then present a proposal for obtaining 3-string interactions from 3-point functionals in Yang-Mills theory in a particular limit of this BMN background, the large mu limit. I will then use this proposal to compute one-loop mass renormalizations of excited string states in the large mu limit of this BMN, of the PP wave string theory. I will then try to match this computation of one-loop mass renormalizations to computations of anomalous dimensions of the corresponding BMN operators. And I will find what at first seems to be a precise agreement with the original calculation, and then tell you about a new puzzle that has to do with operator mixing that is in the unpublished part of this work. Okay, so I first start with a lightning review of the BMN proposal. I mean, perhaps this is not really needed, but I'll do it anyway for completeness. Okay, so BMN proposed that type 2B theory on this PP wave background, this background that looks basically like flat space, except that it's modified by this mass deformation, which makes fluctuations in the 8 transverse dimensions massive. Okay, so that type 2B theory on this PP wave background with a certain Ramond-Ramond flux and a constant dilaton, BMN proposed that this type 2B theory was dual to a particular sector, of the n equals 4, d equals 4 SUN super Yang-Mills theory. Okay, so now I want to remind you of how this duality is made more precise. Firstly, the Yang-Mills theory that we consider is considered in the strict n goes to infinity limit with the Yang-Mills coupling G squared Yang-Mills held fixed, and held fixed at a value that is as usual related to the string coupling constant. Okay, the sector of the theory we consider is a sector of the theory which retains only operators or states which have very large charge, and I'll call this charge J through my talk. So it has very large charge under a particular arbitrarily chosen U1 subgroup of the SO6 R symmetry group of the n equals 4 Yang-Mills theory. Okay, and how large this charge has to be is made precise by the formulas that relate momenta of string states in the PP wave background to charges of the corresponding operators in the Yang-Mills theory. The first formula tells you that P plus, the momentum conjugate to the coordinate x minus, is related to the charge of the operators that you consider in Yang-Mills theory, up to a couple of factors that are finite, and then one factor that blows up in the BMN limit. This lambda here is the Toft coupling, is G squared Yang-Mills n, and goes to infinity in the PP wave limit. Okay, so since we're considering string states with finite values of P plus, we want to consider Yang-Mills operators with infinite values of J. The infinity j going to infinity with n like square root n, so that this right-hand side stays finite. Okay, the second element in the dictionary between momenta and the PP wave background and charges and dimensions of Yang-Mills operators is this entry. It says that P minus up to some rather trivial, finite factors is given by delta minus j. Okay? Since P minus is being held fixed for all states in this PP wave limit, delta minus j of the operators we consider in the Yang-Mills theory is also being held fixed. Okay, so to summarize, the sector of the Yang-Mills theory under consideration is the sector in which the charge j goes to infinity like square root n, but delta minus j is kept fixed, is of order 1. Okay, so as Juan described a few minutes ago, free type 2b theory on this PP wave background is easily quantized in the light cone gauge. And by going through the quantization, you find a certain spectrum of single string states in this theory. Okay, so these are the frequencies of the various harmonic oscillators, and these NNIs are occupation numbers of the various harmonic oscillators. So this is just a sort of small modification of the usual flat space kind spectrum. Okay, the duality that we've just reviewed predicts, and the spectrum formula together predict that Yang-Mills theory in the sector that we've been considering, the sector of large j, scaling like square root n, the Yang-Mills theory in this sector has the following spectrum of single trace operators. These operators are single trace because they're supposed to be dual to single particle states. Okay, so in going from this line to this line, I've just rewritten this formula, but use the dictionary of the previous transparency to rewrite it in terms of Yang-Mills quantities. Okay, so this duality predicts that the spectrum of operators with the large charge, in the sense that we're talking about, is given by this formula here. Okay, so an important point to note, of course, is that this formula is analytic in the Yang-Mills coupling and therefore has a nice Taylor series expansion, and so has a chance of being reproduced by Yang-Mills perturbation theory. Okay, BMN then also went on to identify operators which they proposed would be dual to these string states. Juan has reviewed these operators in detail. I think I will sort of skip that. This is an example of one such operator. You know, these operators are nearly chiral in the sense that they're exactly chiral when all momenta are set to 0, and they're approximately chiral in some local sense. They're almost supersymmetric operators, and that's why they have much smaller anomalous dimensions than you would expect. And BMN proposed that these operators would reproduce that prediction for the scaling dimension. Okay, by now there exists spectacular evidence for the BMN proposal. BMN themselves computed the scaling dimensions of these operators at one loop in Yang-Mills perturbation theory and found, as Juan reviewed a few minutes ago, that their calculation agreed with the string spectrum to the appropriate order. Gross, Mikhailov, and Roybal extended this calculation to 2 loops and also found agreement to the second term in the expansion of that square root. And recently, in a very nice paper, Santambrogio and Zanon gave an argument which, along with some assumptions, was essentially a derivation of that formula, a derivation of the scaling dimensions of the BMN operators in exact agreement with the string spectrum to all orders of the Yang-Mills coupling. Okay. Now, although I've not had the time to review any of these arguments for you, it's important for me to emphasize that all the calculations that were presented here and the Santambrogio-Zanon argument applied to planar computations, to scaling dimensions of operators in the planar approximation in Yang-Mills theory. Okay, now this doesn't, at first sight, this doesn't seem like like an approximation at all, because as we have seen, the BMN limit is a limit in which n is taken strictly to infinity. And we're brought up to believe that the strict n goes to infinity limit is the limit in which you can retain planar graphs and throw away all higher genus terms, all higher genus graphs. So restricting to planar graphs does not seem at first sight to be an approximation. However, if you believe that statement literally, you'd be led directly to a contradiction. You'd be led to a contradiction because, as I said, there's now very good evidence directly from gauge theory that these operators in the planar approximation have exactly the right scaling dimensions to match with free string theory predictions. Yet we know that in general in the BMN limit, the string coupling is non-zero. And so the duality should be one between this Yang-Mills theory and an interacting string theory. So the agreement shouldn't have been so good. You shouldn't have got perfect agreement with free string theory. So we must have been forgetting something somewhere in our field theory calculations, and it's sort of clear what we have been forgetting. I mean, the usual Toftian philosophy tells us what we've been forgetting. We've been forgetting string interactions, so we've been forgetting non-planar graphs. So somehow non-planar graphs must continue to contribute, even in the strict n goes to infinity limit, and of course that is true. To convince you of that, I'll start by doing a little counting. Okay, I'm going to consider the operator trace z to the power j, and trace z. I'm going to compute the 2-point function of the operator trace z to the power j, z bar to the power j, at the planar in the planar approximation and at genus 1 in free Yang-Mills theory, and this computation will show us something quite nice. Okay, first let's do this computation in the planar approximation. Okay, this operator here has j lines emanating out from it. These jz fields. This operator here also has j lines emanating out from it. Okay, if we want planar contractions, we have j choices about which line to contract, let's say this guy with. Okay, so there's a factor of j, and then planarity fixes all other contractions, and so on. Okay, so this thing is ordered j. It's also proportional to the n to the power j from usual Toft counting, and then you get all the factors of your j propagators. Okay, so in the planar approximation, in free field theory, this is exactly right. Okay, now what I want to do is to try to extend this calculation to one higher order in the genus expansion of Yang-Mills theory. So I want to do these free contractions on the torus in Yang-Mills theory. Okay, so this is also rather easy to do. Let's draw a torus, and let's draw the two operators, each of which has j lines emanating out from it, for which we want to do these free field contractions. We want to look at all contractions that can be made on the torus, okay? And so these contractions actually can be made in 4 different ways. There are the direct contractions that go like this. There are contractions that go across this cycle, contractions that look like that, and then there are contractions that look like this. You might have thought there was a 5th contraction that went like that, but actually that overlaps this contraction because all these 4 points are the same point on the torus. Okay, so redrawn in terms of sort of more familiar looking notation, if this is one of the operators and this is the second operator, we have sets of lines that go like this, sets of lines that go like this, that, like that, where, okay, I don't have the time to say this more thoroughly, this is one of the operators, this operator here, this is the second operator here, this is this set of lines, and so on. So all of everything that I said in detail is summarized here. These are the the planar contractions. These are the contractions on the torus. They're drawn more nicely here. These 4 groups have been labeled more carefully on this diagram here. And now, having looked at all the diagrams that you can draw on the torus, I sit and count them. Okay, it's easy to count these graphs because in order to find all the graphs that you can draw on the torus, what you have to do is to divide up your j lines into 4 different groups. These 4 groups here, okay, these 4 groups that you're contracting in these different ways. And then in addition, you also have the factor of j from cyclical rotations that you also had for planar graphs. Okay, so you get a factor of jc4 plus an extra correction of jc3, which I won't bother you with. It's subtlety which won't matter in the j goes to infinity limit. So you get in the leading large J behavior is j to the 4 by 24 times j. So j to the 4 by 24 times the planar correction. Okay, so we've concluded that at genus 1, the number of graphs that contribute at genus 1 is of order j to the 4th. Okay, this genus 1 graph can be redrawn in a slightly cleverer way by choosing the 2 points at which we put the operators to be the center of the torus and this point, which is also the same as these points. I've done this so that you can easily generalize this argument to genus 2, which is basically an 8gon where you put one operator in the middle of the 8gon and the other operator on all these vertices which are all identified. You can easily see that by extending the argument I gave you, you would get j to the 8 graphs that contribute at genus 2 and so on. Okay? So we've concluded that the number of graphs that contributes at genus H scales like j to the power 4h. Okay, so why was that important? That was, okay, so of course now you see the logic. Each graph at genus H certainly contributes at order 1 over n to the power 2h as we expected. Okay, however, the number of such graphs, okay, as we've just argued, scales like j to the power 4h. Okay, therefore the net contribution from all graphs at genus H scales like j to the power 4h divided by n to the power 2h, or g2 to the power 2h, where g2 is j squared by n. Okay, so the correct genus counting parameter for Yang-Mills theory is not 1 over n squared, but j to the 4th by n squared. Ordinarily, in the usual large n limit, this does not matter. In the BMN limit, this is very important because j is being scaled to infinity as n is taken to infinity. Okay, so now, do we have any good reason? Well, so higher genus graphs we argued should be related to string interactions. Do we have any better way of seeing that? Certainly we do. One immediate indication that this G2 is a parameter that governs string interactions is obtained by rewriting it in string theory units. G2 in Yang-Mills terms is simply j squared by n, but rewritten in terms of string theory variables, it turns out to be gs squared times mu p plus alpha prime, the whole thing to the 4th. Okay, this can be rewritten in a nice way. This is gs squared alpha prime to the 4th divided by L to the 8th, where L is 1 over mu p plus alpha, 1 over mu p plus square root, which is the length scale of confinement of modes moving with momentum p plus, the length scale at which they're confined to the origin in transverse space. Okay, so this is the effective compactification radius for all modes moving with momentum p plus, and consequently this quantity here is the effective two-dimensional Newton's constant that governs the gravitational interactions of these modes. Okay, so our quantity G2, the effective genus counting parameter of Yang-Mills theory, is very precisely the effective two-dimensional Newton's constant of the corresponding modes in the string theory. Okay, so this is the general framework for how non-planar graphs are going to relate to string interaction effects, but of course I want to make all this much more precise. Okay, so to start with, so I'm going to now start this course of making everything a little more precise. Okay, so to start with, I'm going to give you a prescription for relating 3-point interactions in light cone string field theory, 3-point matrix elements of 3 string states, or the matrix elements for a single string to go into 2 strings in light cone string field theory. I'm going to try to give you a prescription to relate this matrix element to a calculation you can do in gauge theory. Okay, so well, as motivation, I first remind you that light cone string field theory is well defined and computable in this PP wave limit. And just recall the structure of usual light cone string field theory. You have 2 strings on one side. Their lengths go from 0 to p1 plus, and let's say the sigma coordinates go from 0 to p1 plus and p1 plus to p1 plus plus p2 plus. Similarly, you have the third string, its sigma coordinate goes from 0 to p3 plus. And in order to find the interaction matrix elements of that allow you to connect this one string to these 2 strings, the matrix elements of the light cone Hamiltonian between these 2 states, in flat space, this is the prescription that was discussed in detail by Green-Schwarz and Brink in the early 80s. The prescription says take the three wave functionals of the first quantized states of the strings in question, okay? Do a path integral over their x coordinates for all values of sigma. When these wave functionals are convoluted by a particular prefactor times a delta function that sets the value of x at any given sigma to be equal to the value of x at the same sigma for the top two strings and the bottom string. Okay, so this is the general structure of light cone string field theory in flat space. Now Spradlin and Volovich have in a detailed algebraic analysis have basically shown that this structure remains unchanged even in the PP wave background. Okay, now our proposal was that this matrix element can be computed in Yang-Mills theory, through the at large, well, to first order and lambda prime, which is g squared Yang-Mills n by j squared, which is also 1 over mu squared, so large at small lambda prime or large mu, can be computed in Yang-Mills theory by the following prescription. Consider the 3-point coefficient of normalized, the coefficient in the 3-point function of normalized BMN operators. So that's what I've called C1, 2, 3 here. Multiply that coefficient by the difference between scaling dimensions of the sum of the first two operators and the third operator that we're interested in. Okay, multiply the whole thing by mu, and to leading order in 1 over mu or to lambda in lambda prime, we propose that this formula gives you the translation between string interaction effects and 3-point functions in Yang-Mills theory. Okay. Okay, I should elaborate this proposal in several ways. Firstly, why was this? Firstly, I want to make this proposal sound reasonable to you at first order. Recall that just ordinary matrix elements between states by the state operator correspondence maps to correlation functions of the corresponding operators. Okay, what we're after is matrix elements between states with an insertion of the light cone Hamiltonian. So it might seem reasonable that such objects would be related to a correlation functions of the corresponding operators times some factor that's linear in P minus. Okay, in order to see what linear factor in P minus we have to use, we note that all interaction effects should go to 0 when Yang-Mills couplings go to 0, because we know that anomalous dimensions all go to 0 in this limit. So mass renormalizations, for instance, must go to 0 in the limit that G Yang-Mills squared goes to 0. And that basically uniquely fixes the linear factor in P minuses. It has to be the sum of the first two dimensions minus first two P minuses minus the third P minus, which is the same thing as mu times the sum of the first two dimensions minus the third dimension. Okay, so I'm sorry for going so fast, but that's limitation of time. Okay, so this is the okay. This was the base, the 0th order motivation for our proposal. Okay, you can check that our proposal gives you sensible scalings. You know, the quantities that we've written down all scale in some way with n and j, and in order for this proposal to be a proposal that might make sense, these quantities should all have good large n scaling limits. I don't have the time to review that for you, but you can check that that's true. Okay. An important point to note is that according to our proposal, matrix elements between on-shell excited string states, between string states of equal energy on the two sides of the matrix element that you're taking vanish. And this implies that excited string states are stable to the order that we're considering. This will allow us to actually compute, to compute the mass renormalization of excited string states. So the question has good meaning. Okay, fine. Now I wanted to take you through a detailed comparison between our proposal and light cone string field theory, but for lack of time, I will sort of just tell you the result. in a sort of detailed calculation, Spradlin and Volovich have actually gone ahead and computed the matrix elements in light cone string field theory between the corresponding string states. And they find we of course went ahead and did the relevant Yang-Mills computations in free Yang-Mills theory. The two sides have been explicitly computed, and the comparison is in perfect agreement with our conjecture. Okay. So now that we know about interactions between string states, we can go ahead and try to compute some physical effect. Okay. So one nice thing you could try to compute is the one loop mass renormalization, the one loop mass normalization of an excited string state. Okay. So what are we doing? Okay. I've given you the matrix elements between one particle and two particle states in the string theory. It's now simple to use second order perturbation theory, quantum mechanics, second order ordinary quantum mechanical perturbation theory to compute one loop mass, to compute shifts of energies at second order in perturbation theory. This matches to a one loop mass renormalization of the corresponding states. Okay, so we have all the ingredients necessary to do this calculation. We use the standard formula of second order of perturbation theory, and we find the following answer. Okay, it's an answer whose parametric dependence makes sense. It's proportional to G2 squared, the genus counting parameter squared, because it's a one loop genus 1 effect. It's proportional to lambda prime because it has 1 power of the Yang-Mills coupling, and the rest is not something you could have guessed, but is obtained by explicit calculation. Now, you might wonder if there's a more direct way of covering the same mass renormalization theory. And if you do the naivest thing possible, you land right on your feet. Okay, so suppose you take the BMN operators, the operators that I reviewed for you earlier in my talk, and you compute their 2-point functions, but including effects at genus 1 in Yang-Mills theory. Okay, so BMN themselves computed the anomalous dimensions of these operators to one loop in Yang-Mills theory, but only retaining planar graphs. So that's this term here. Adding in genus 1 effects gives some additional normalization at all for these dimensions, but also an additional coefficient in front of the log. Okay, so this additional coefficient would most simply be interpreted as an, and it might look familiar to you because we've seen exactly this formula before. Exactly this formula was obtained from the mass renormalization of the corresponding state using perturbation theory in Yang-Mills theory. And the two calculations, though they agree, the answers agreed completely, the two calculations had a very different form. You know, it wasn't at all clear to us until they did agree that they would agree. Okay, I want to use my last 1 minute, my last minus 2 minutes to present you an unsolved puzzle. Okay. Okay. Right. An important unsolved puzzle in this whole story. And this is the puzzle. You see, it turns out that explicit calculations with these Yang-Mills, with these operators show that the BMN operators, once you include order G2 effects, are not good operators, not operators with good scaling dimension. You can actually explicitly calculate the operators with good scaling dimension, and there's some linear combinations of the original BMN operators with double trace operators. Now, taking into account this effect and computing the scaling dimensions of these good operators, the operators with good scaling dimensions, we get an additional piece to the scaling dimension. This is the part I presented in the previous transparency. We get a new piece here. Should say this is tentative results from recent calculations. These are unpublished and might change, but I think this is probably right. Okay, so now we have a puzzle. We have a puzzle because now the two sides of our story don't agree anymore. You know, this additional piece was not there in the Yang-Mills, in the second order perturbation theory, and okay. So, okay. So I conclude and ask for questions.
It's on? Yeah. I'm Tom Banks from Rutgers in Santa Cruz. Shiraz, the ADS theory has a discrete spectrum, and it doesn't really have a scattering matrix interpretation. In flat space, string theory has a scattering matrix interpretation. The PP wave theory has a continuous spectrum. Do you think it has a scattering matrix?
Okay, so the question is, do I think the PP wave theory has a scattering matrix? I should say that I don't have a very clear opinion on this, but I'll give you my opinion. If you look at a wave packet for particles moving in this PP wave geometry, these wave packets separate. They can separate because in these two dimensions, you've got a non-trivial dispersion relation between P plus and P minus, so different particles have different phase velocity, so wave packets would separate. So this makes it sound like particles can separate in as much as they can always separate in two dimensions. Usual two-dimensional field theories have S matrices, so I would naively I would tend to think, why not? However, many things make me unsure of this argument, including the fact that the Penrose diagram of the PP wave is rather odd, and it doesn't easily lend itself to interpretation of scattering from Scri plus Scri minus. So I'm not completely sure. That's my answer. But maybe somebody else in the audience, maybe Juan has a. Well.
I want to ask a different question. What? Oh yeah, I'm Juan Maldacena from the Institute of Advanced Study. So the result you had in your previous lab transparency was the gauge theory result, right?
Yes.
Where you consider the two-particle state and the single particle state, right?
This result?
Yeah, that's right. Was that a perturbative gauge theory result?
Yes.
Okay.
The result from perturbative gauge theory, it's the anomalous dimension of...
Yeah, I understand. Now, in the corresponding string theory, wouldn't you also have to have the problem that the good eigenvalues of the Hamiltonian are not the free string, eigenstates of the Hamiltonian are not the free string states, but you can have two string states plus the single string state and so on?
Exactly. Ordinarily perturbation theory, ordinary quantum mechanical perturbation theory takes that into account. Because the formula I used was the formula to find the energy of the eigenstate, whatever it is. Right. So naively, that should have been taken into account by that formula. Now, there are various possibilities for ways in which it could be fixed up. And one possibility that was suggested by Hermann Verlinde is that there could be new explicit terms in the Hamiltonian at order G2 squared that take one string to the next. These are contact terms that sometimes appear in string field theory. That contact term might be exactly this new term. Another possibility is that we might have missed some intermediate states in our quantum mechanics calculation. Naively, these are the states I considered were all that there were, but it's a possibility for some subtlety. So there are some ways